integer coefficient. We don't deal with rational or real numbers. Everything here is integer. Good? Okay, so let's move on. Oh. Sure. Sorry. All right. Can you hear me? Okay. Now, let's move on. Any questions? Yes?
So what's the head mean?
Yeah. Yeah, what does the head mean, right? So I encourage you to read a book by, I forgot the name, Constantine. The book title is Computational Homology. So let me just give you a really quick answer. V hat really means a bijection between, this is really a map. This thing really is a map from this topology space to there. Right? So it's abstract thing. Okay? You can write down rigorously, but for now, you just think about this as a standard basis. Whenever I have a vertices in topology space, I associate with like a standard basis in the algebraic world. That's how you can think about it. Okay. All right. So I can erase this. I can keep going. Okay. So keep in mind the goal. The goal is to somehow extract this information, to extract the circle information. We are really close. So let's keep doing that. So now I have the group. I have the C0, and we have C1. This is called a chain group. This is called a chain group. This is very classic theory in algebraic topology. It's not like I invented something. This is very classic, very elegant chain group. So now what I want is I want to find a relation between the chain groups. I want to find a relation between C1 and C0. At the end, I hope that will help us to understand the shape of this thing. Okay? So now what I want is to introduce the relation between the chain groups. Okay? And this relation is called a boundary map. Right? So I'm going to give you one more thing, the boundary operator. Okay. What is a boundary operator? Very intuitive, right? In the topology world, if I have a point, if I have a vertex, what is the boundary of a vertex? Well, nothing, right? Because a point, you cannot talk about the boundary. So a boundary of a vertices will be an empty. What about a line segment? A boundary of a line segment will simply just be the endpoint, right? So let me say A and B. The boundary will be the union of A and B, the endpoint. Okay? Oh, yeah. Now, in the algebraic world, I'm too short. Okay. In the algebraic world, how does that represent the algebraic world? Okay. So in the algebraic world, I'm going to write, I'm sorry, I have to move up. Okay. This is the endpoint, all right? This is not very special. Okay. So the boundary of a vertex is, right? So I'm going to use 0. The boundary of a vertices, that's my vertices. According to this, right, boundary of a vertex will map to 0 very naturally. Right? Because you cannot talk about boundary of a single point. So I map that to a 0. What about a boundary of a vertices? what about boundary of a vertex? Okay. So for instance, a boundary of E1, according to this thing, it's going to be just the union of the endpoint. The endpoints, right? So this is the endpoint. Collection of the endpoint. So in this case, what is E1? E1 consists of the line segment V1 and V2, right? So the endpoint will be V2 minus V1. So here I imposed an orientation, right? This is somehow artificial, but as long as you keep it consistent, you'll be okay, okay? So here I'm going to follow this orientation. So I can define the boundary map in this manner. The endpoint, V2 minus V1, just like how you define a vector, the endpoint, V2, ending point minus the starting point. That's how you can define a boundary of an edge. Okay? Similarly, the boundary of E2 will be V3 minus V2, correct? V3 minus V2, and the boundary of E3, can you help me? What would that be? V4, right, V4 minus V3, thank you, right. Lastly, yes, the lastly E4 will be V1 minus V4. Okay, that's how you can do it. For V1 minus V4. Okay, good. Any questions at this point? All right, good. Good. All right. And now maybe let me ask you, why do I only care about the basis? Because from the linear algebra, if you want to look at the linear map, it's enough just to look at the basis, right? What the basis maps to. So now I know this map, the basis maps to this, the basis maps to that. I know how this thing works in general. Come again?
We assume that operators are linear.
Yes, yes. Well, we define this way, so it will be linear. Yes. Okay. All right. So what this means is now we have a linear map from C1 to C0. This is a boundary map. Okay. This is a linear map. Right. So really, really close, right? So now we not only have a vertices and edges information, we also have the relation between edges and the vertices, right? That's the reason why we bring algebra into this thing, right? Because now you can talk about the relation between edges and vertices, okay? Okay, very good. In fact, I'm not only having this, I'm going to have the chain of this thing, right? So I'm going to have C2, this is the boundary, C1, C0, 0, and here, like this. Right? So in the algebraic topology world, this is called a chain complex. Right? This can be infinite long, but only finitely many are non-trivial. So in this case, this can go on forever, but all of them are zeros. Right? The only non-trivial happen in C1 and C0. Everything other will be 0. But there is a benefit of writing this, so we just keep it this way. Right, okay, good. Now I want you to look at this thing here. Right? I want you to look at this thing here. As you remember when I was in high school, my teacher told me a trick to solve some problem, right? The trick is whenever you see the things like this, if you sum all of them, you will see 0, right? That's what happened here. If I sum equation 2, 3, 4, and 5, what do you see? What do you see? Cancel. V3 cancel. V4 cancel. V1 cancel. So you end up with 0. Good? Good. So here is the remark, the very important remark. What do you see if I sum all of them, E1, blah, 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 until E4, you have a 0. Good? And now let's go back to the topology world. What does E1 plus E2 plus E3 plus E4 mean? E1 plus E2 plus E3 plus E4, that's exactly the cycle we're trying to capture. Okay? Good? E1 plus E2 plus E3 plus E4, that's exactly the information we need. Okay? So how do we... Okay, I can keep that. So how do we measure the holes? To measure the holes, it can be captured from this boundary map, right? This is a linear map. You map something to 0. That element is in what? Huh? What's that special name? Kernel, exactly, right? So kernel is what we are interested in. You have a map, linear map, row 1. This element maps to 0. So here's the definition. We are interested in the cycles. This is called the cycles. This is defined to be the kernel of the boundary map. Okay? Okay. And then there's another thing called the boundary. Boundary is very intuitive. This is going to be the image of the boundary map, right? So this is like redundant, right? This map is called boundary. Therefore, the image of this map is going to call the boundary map. Okay. So now we have the idea how to capture the circle, how to capture this information. It's going to be somehow related to the kernel. Okay? But here's the thing. What if my cycle happens to be someone else's boundary? Then that's not the real cycle I'm interested in. So let me give you one example. Suppose I'm looking at a disk right here, right? This is going to be my cycle, but this cycle happened to be this face, the boundary of this face. So that's not the actual cycle I'm looking at. Cool? Therefore, finally, we define the homology group. Homology group of that set is going to be the cycles. Okay? We are interested in the cycles, but we are only interested in the cycle which is not someone else's boundary. Okay? This is a cycle, but that happens to be a boundary of one layer up. This is the faces, the two-dimensional object. Okay? Therefore, this is the homology group. Right? The cycles model the boundary. This is the homology group. Yes. Good. Questions? Yes. Okay. Right? So this is called the homology group. Homology group. And we can go back to this. What is the Beatty number in this case? Well, Beatty number will be the rank of the homology group. Okay. Good. So this is the definition. So the Beatty number will be the rank of the homology group. Right. Okay. So after 1 hour, we rigorously define the Beatty number. Right. This is how this intuitive thing go into the math. Okay. So Beatty number count the case dimensional whole is defined through homology group. Okay. Let's go back to this example. Let's finish this example. So what we have is we have the chain group of this object C2, C1, C0, 0, you stop here. Okay, you stop here because nothing there. What is C1? C0 is the span, the linear combination of those four bases. So this isomorphic to Z4, right, because I have 4 freedom, or the number of bases is 4, so that isomorphic to Z4. Similarly, this is isomorphic to Z4 as well. There's no C2, there's no faces in this example. So this is isomorphic to the trivial group. And we have the relation between the chain groups. I have the relation between row C2 and C1. I have the relation between C1 and C0. I have the relation between C0 and 0. Okay. Good. And this row business is the boundary map defined in this intuitive way. Okay. And the question you should ask is, okay, this is a very toy example. What happens if I have 4-dimensional cube, or maybe just 3-dimensional cube? How do you write down the boundary map? Okay, so that's what the textbook and some other people was working on. There is a way you can define the boundary map. It's a formula actually, so you can define the boundary map for arbitrary dimension of cube. So the theorem is complete. Okay, but let's just keep looking at this. Now I have this relation. I have a boundary. What we really care is, okay, so now we really care about this, right? So here we go. So let's take a look at this thing here, C0, right? H0 equal to the kernel, let me write really slowly, 0 cycle mod out the boundary 1, which is the kernel of this row 0, mod out an image of this guy. Good. And H1 will be cycle mods out the boundary, which will be the kernel mods out and images. Okay. And the rest is not important. And at this point, you notice, all right, in order to find out what this group looks like, I will need to know this, the image of row 1 and kernel of row 1. In fact, you need to study the entire map, row 1. Okay. But thanks to linear algebra, we can do it efficiently, right? Okay? We can do it really fast. How do we do it? Linear algebra concerns matrix, right? So now I can write any linear algebra course will give you the class, the lecture on how to write a linear map to matrices. Exactly same thing over here. I can write boundary map as a matrix. Ready? So now this is V1, V2. I can have like V1, V2, V3, and V4. So the first column will be negative 1, 1, 0, 0. And the second column will be 0, negative 1, 1, 0. And the row column 3 will be 0, 0, negative 1, 1. And the last one will be 1, 0, 0, negative 1. That's the boundary map written in matrix. And now, what do you need to know? You need to know the kernel. You need to know the images. Okay? In fact, we only care, in the current application, we only care about the Betti numbers. Right? We only care about the Betti number. So really, you only care about the rank. So how do you find out the rank of a kernel, and how do you find out the rank of an images? Right. There's no magic, right? Gaussian elimination, or matrix row operations. Right? You do row operation on this thing, you find out the pivot, you find out the free variable that determines the dimension of images and kernels. Cool? Good? So from here, you can do row operations. You can do row operations. And because everything here is integers, so there is a special format. This is called the Smith's normal form. And this is what actually in the code we're going to use on Monday. Okay? Smith's normal form. A quick way to explain this is the integer version of Gaussian elimination. Okay? So you can do row operation on this integer matrix with integer coefficient. Okay? So I will skip all the details. I'm just go through in our mind. Let's do it. You can do the row operation. You can also do the column operation, whatever familiar with you. If you want to do row operation, you multiply this. You add the first row to the second. This will cancel. You move on to the second stage. That's how you do it. And you can find out the pivot. That will be the dimension of image. And the number of free variable will be the dimension of kernel. Cool? Okay. So you can actually do it. This will be your exercise. You will find out the dimension. You will find out the kernel of row 1 is isomorphic to Z. This is exactly this thing over here. This is the base. This is actually the basis of this guy. Okay, you cannot find any other this, but anyway, you can also do it using the Smith's normal form or row operation to obtain the same outcome. This is more from the intuitive way. This is more algorithmic way. And then you can also find out the image of row 1 is isomorphic to Z3. And by the most famous theorem, you know this is a Z4 map to Z4, so the dimension should be matched, right? Okay. Cool. Therefore, here, the kernel of row 0, you map everything to 0. So the kernel will be 4 space, Z4. Mod out the image of row 1, that's going to be Z3. So this will give you Z. This is isomorphic to kernel here. Z. An image of row 2, you 0 map to non-trivial. The only thing you can map is 0. So the image of this thing is trivial. So this will give you Z. Okay? So the homology group of this circle, so this is what people will write. The homology group of a circle, this is my circle, equal to Z if K equal to 0 or 1 and trivial group otherwise. Okay. And apply our definition. The definition, the Beatty number defined to be the rank of the group. So the rank in this case is the rank 1. And that's how you see there. Okay? Any questions? Okay. Good. So this is what happened in practice, right? You have an object, right? The real world object. You want to represent in a way so that the computer can do things, right? So one common thing is maybe you want to measure some, I don't have something. Maybe you want to know the texture. Oh, okay. Look at the flow. The flow has some certain textures, right? Maybe you want to measure how complex, or maybe you want to measure what is the complexity of this flow, right? So what you do is, okay, I take the picture, I take maybe a digital pictures, right? Now you have a digital pictures, then you have to, produce somehow a binary images, and then you can go through this whole thing to compute the Beatty number. Okay? Good. And everything here, we have the theory support. Not only we have theory support, we also have a very fast algorithm to do the Smith normal form. So you can look at kernel, and so you can calculate the homology group very fast, and therefore you can compute the Beatty number very fast. Okay? Cool? Yes, I have a couple more minutes. So I'm going to conclude with one example, one application.
So if you
yes.
do the higher dimensional homology theory can also be used to do some computation in linear algebra?
Yes, exactly. Yes. Yes. So you have a complexes, everything now become a matrices. Now you have a matrices, you do the normal form, and that's how you can compute the Beatty, the homology group, and therefore the Beatty number. Yes, if you have a higher dimensional object, you still follow the same pipeline. Very good. All right. I want to conclude with one simple application, and we will stop, and then we will talk about persistent homology on Wednesday. Okay? This application is called the sublevel set approach. This is very common in image processing, like classification point. All right. So let me give you a 1D example. Suppose I have a function like this. Okay, let me do this very simple example. Right, suppose this function is called x squared. Well, okay. What is said is said. All right, so if I want to do x squared, right? So what to do in computer, right? First thing is you discretize this one-dimensional map, right? So for instance, I maybe discretize this to be from -3 to +3, maybe, okay? So I can do it a very small grid. Uniform grid, that's just to be very consistent, right? Cool. So this each box, each grid here is a number, right? So this might be +9 related to this value. This might be 8 point something, and this might be 4. This will be 0, and so on and so forth. Cool. Right, so let me just made up some number. So now you have an array of a number like 9, 8, 7, 4, 0, 4, 7, 8, 9, something like that. Right? Cool? Cool. Cool. Okay. So this is actually what you will collect when you have the data. What you see is you have this all the grid point 9, 7, 4, 0, blah blah blah, right? Combined with the x location, you might be able to approximate this function. Okay, that's this. Okay, good. And this is called a sublevel set. I think many of you already know what the sublevel set is. Sublevel set defined to be this function. It is a set less than equal to this value t. Right? So it's the collection of x such that f of x less than t. That's the sublevel set. All right. So in this case, for instance, F0, in this case, everything is greater than 0, so you're going to only have those points, one point there, right? So F0 will be just like 0. Cool? And F1 is nothing, but F4, you're going to have 4, 0, 4, so those three boxes are grouped together, right? So in a way, you can think about is when t equal to 4, this box grew from 1 box to 3 boxes. Cool? So when f equal to 4, you're going to see the 3 boxes. Okay? And so on and so forth. Cool? And what you observe is this is a one-dimensional example. You can imagine if you have two-dimensional function, three-dimensional function, you know, the principle is the same, but this is the concept I want to show you, right? So as t increases, what you will see is a sequence of sets, right? So you have F0 is a subset of F4 in this case. It's going to be a subset of F7. It's a subset of F9, 8, and, well, let me just write down, and the subset of F9. Is that cool? Yes. This is just one-dimensional example, right? You have two-dimensional example. Good. This is called the sublevel set method, and some other early development is called size function function, a size function technique. All right. Now you create a sequence of level set, a sequence of a set. Right. So now what you do is you can do a lot of things. For one thing, you can compute the Beatty number for each. You can compute the Beatty number for each level set. Right. Then you have the like a Beatty number curve of this object. Cool. Right. So I will give you more detail on maybe on next Wednesday. So, but this is a very common technique in image processing. So in the one application, people try to classify the sign languages, right? So you have like this will be 7, sign languages. There's a international universal sign languages. They use this technique. They were able to classify. Okay, what is this sign represent? Okay, that's called a size function. And this is really the foundation of the persistent homology, because let me give you a really quick idea. For each set, you can compute the homology. Right? So for each set, you can compute the homology. And because of the inclusion, right? So now I want you to imagine for each set, I have this sequence. For each set, you have a sequence. For each set, you have a sequence. Right? So really, you have a net of a sequence. And because of the inclusion, you have the relation from those first column to the second column. Right? Okay. So in a way, you can compute all of the homology. Not only that, you can compute the Beatty number. Because of the inclusion, you can also track how the feature changes, how the topology changes over time. Okay?
This is more like a Morse function.
Yes, yes. That's why in the beginning it related to the Morse function. Yes. Okay. And I will go more detail next time. And thank you very much. And I will take any questions you may have.
Computer-aided proofs.
Yeah.
That you mean something different than what people do in homotopy type theory, right?
Yes. Yeah. So for the computer-assisted proof, it's more analysis, and this is more data analysis. You have the data, you try to analysis the data. And the computer-assisted proof is really just to prove the existence of the solution.
I mean, there are kind of very known direction in mathematics where people try to prove things using computers. They use system provers like Coq.
Yes, yes.
Another approach there in that area, although minor, but anyway, is using homotopy type theory,
yes,
which is kind of, in a sense, algebraic topology transformed to type theory. But the example you brought at the beginning of your talk, as I understand, is something different than homotopy type theory. You were talking about some different approach?
Well, I think it will be related to homotopy type, and it is also related to the Morse theory, the Conley index theory, or like the fixed point theory type.
So it's something different. People use these exactly computational topology to verify something related maybe to differential equations.
Yes.
Could you provide maybe the surname?
Yeah, I can do it. I can show you some names.
Because I'm not interested in things like homotopy type theory, but in more practical verifications, maybe.
Yeah.
It would be interesting to look for.
Yeah, I can send you some. Yeah, I can definitely send you some. Yeah, I think in their paper, a lot of work is For instance, you have given a given a dynamical system. You want to prove whether this PDE has a unique solution, just say this way. And what they do is they transform that PDE into a zero finding problem. Right, so you need to use some sort of fixed point theory to prove, right? And then how do you provide the fixed point? They're gonna use the Morse theory and the Conley index theory to prove that. So that's basically what happened there. Okay. Yes?
Some researchers might use C2 to replace the coefficient C.
Yes.
To make, so is
Yes.
there any advantage for this treatment? So
Yes, that's a very good point. So here I'm just really doing very, very naive way. In fact, the coefficient, what you can do is, just like you said, you can do the Z2 coefficient. Right, so you don't have to, but because really what you really care is like this. So you can do, in fact, I think many software take advantage of the Z2 coefficient because that's so much faster than the integer. Because you only have 0, 1, 0, and 1, so that will be really fast. So if you do the Z2 coefficient, then you don't have to worry about the orientation. So the orientation is dropped, everything can be done, yes. So here I'm just presenting a way, but certainly you can do. Yes, yes. Everything I present here will be equivalent. Yes. Okay. All right, so I will thank you for coming today, and I will see you on Wednesday. Thank you.